first, okay? So when we're making something new, when we're making a recipe, we have to follow a specific set of instructions and follow a specific set of ingredients, okay? Just like in a chemical reaction, we have to put in certain amounts of certain substances if we want to get our ending product, okay? So when we look at what we're trying to make, and we're trying to determine this recipe we want to follow, we have to make sure that we have the correct number of ingredients. Okay, we have enough sugar, we have enough flour, we have enough whatever we're making, okay? If we don't have enough of it, that's going to limit the amount of cookies we can make, or limit the amount of whatever we're making, okay? If you are going to make cookies and you need 4 cups of flour and you only have 2 cups, you can only make half the amount of cookies that you want to make, right? Does that make sense? So flour in that case would be what we call your limiting reactant. Okay, it's limiting the amount of product that you can make. So we're going to look at a recipe today for a double cheeseburger. Okay, we're going to look at the ingredients that go into it, the ratio of ingredients that we have to have in order to make a successful double cheeseburger. Okay, so you don't necessarily have to take notes on this part of it. I'm just trying to introduce it to you conceptually so you understand kind of what we're going through, and then we'll look at the chemical side of it. Okay, so these are the things we need to make a double cheeseburger. We need 1 hamburger bun, a tomato slice, lettuce, 2 pieces of cheese, and 2 hamburger patties. Okay? These are the things that you need to make a successful hamburger, okay? Or a double cheeseburger. These are the ingredients that we have to have. If we don't have one of these ingredients, we can't make what we want to make, okay? So if we want to make 5 double cheeseburgers, how many of each of these ingredients do we need? Okay, if we want to make 5 double cheeseburgers, we need 5 hamburger buns. Okay? If we want to make 5 double cheeseburgers, how many hamburger patties do we need? We need 10. How many slices of cheese do we need? 10. And how many slices of tomato do we need? 5. Because each serving just gets 1 tomato slice.
What are you making, a hamburger salad?
Just this one that we're looking at here, we're looking at a specific ingredient list. All right, so now we're going to look at the number of ingredients we start with, and we're going to determine how many of our product we can make. Okay? So if we start with 1 bun, 2 patties, 2 slices of cheese, and a tomato slice, how many double cheeseburgers can we make? 1. Yeah, I know. We're going to ignore lettuce. Okay, I know. We're going to ignore lettuce. We'll say we have just like infinite lettuce. Okay, we have plenty of lettuce. All right. So we can only make 1 double cheeseburger if we start with these ingredients. How many can we make if we start with the second set of ingredients? We can make 2. Okay. How many can we make if we start with 1 mole of buns, 2 moles of hamburger patties, 2 moles of cheese, and 1 mole of tomato slices? We can make 1 mole of double cheeseburgers. That's a lot. That's a lot of double cheeseburgers. Okay, that's like 10 to the 23rd double cheeseburgers. Okay, that's a lot.
But wouldn't 1 mole of patties be 4 patties? Or wouldn't 1 mole be 1 mole of patties would be 2, and then 2 moles?
No.
But isn't a mole like from the original mole?
Yeah, we're still just looking at 2 moles of patties. So 1 mole of patties would be 6 times 10 to the 23rd hamburger patties. 2 moles would be times 2. Yeah. Yeah. All right. So how many can we make if we start with 10 buns, 2 patties, 2 slices of 10 buns, 20 patties, 2 slices of cheese, and 10 tomato slices? We can only make 1. Okay, why can we only make 1? We can't make more than 1 double cheeseburger with our ingredients listed. Okay, the last set of ingredients we ran out on our assembly line at the cheese station. Okay, so slices of cheese is going to limit the number of our product that we can make. Does that make sense?
Yep.
Okay. Okay, if one of our ingredients or one of our reactants gets used up during the process of our preparation or the process of the reaction, it's called the limiting reactant. Okay, because it limits the amount of product that we are able to make. So as we're going down our assembly line of making double cheeseburgers, we ran out after 1 of cheese. Okay, we ran out of cheese after making 1. So that means it's done. It's over. We can't make any more. Okay? So in this case, the cheese was our limiting reactant, which I abbreviate with an LR. Okay? So here we're going to look at how this kind of applies to chemistry and to chemical reactions. When we're doing a chemical reaction, it's important to us to have the exact right amount of each of our reactants going in, or our ingredients. Okay, think of our reactants or things on the left side of the chemical equation. Those are kind of our ingredients for our chemical reaction. If we don't have enough of a certain substance, we won't get as much product as we would like. Okay, so we're going to start looking at some calculations to determine which of our reactants is our limiting reactant in chemical equations. Okay, we're going to be able to determine from two different starting amounts which one will be our limiting reactant. Okay, which one will run out of first. Being our recipe now. So RXN, that's my abbreviation for reaction. Okay, so a chemical reaction is now kind of our recipe. We have to have a certain number of reactants or a certain number of ingredients to go in if we want to make a desired amount of product. So all this stoichiometry that we've been doing has been assuming that we have a perfect reaction that goes all the way to completion with no running out of either of our substances. Okay, we're assuming that one product or one of our reactants goes in with excess of another. So we're going to assume that what we've been doing so far has been one of our reactants going in with the other one being in excess. Like we had unlimited lettuce in our previous talk, that would be like unlimited of this other reactant. So that's what we've been doing thus far. Now we're going to look at a given amount of both of our reactants, and we're going to see which one will run out first in our chemical equation. Okay, we're going to look at the formation of ammonia. Ammonia is our NH3 here. So this is our balanced chemical equation for the formation of ammonia. What type of chemical reaction is this? Synthesis. Since two things become one, synthesis. Okay? So what this is telling us is that when 1 mole of nitrogen gas reacts with 3 moles of hydrogen gas, we can get out 2 moles of ammonia. Okay? When 1 mole of nitrogen gas reacts with 3 moles of hydrogen gas, we can get 2 moles here. That has to be the ratio in which these things are combined. Okay? So let's look at this. If I want to form ammonia, but I have 2 moles of nitrogen gas and I have 3 moles of hydrogen gas, how much ammonia could I form? Okay, so how many of you think 1 mole? How many of you think 2 moles? How many of you think 4 moles? Just think it over and then I'll survey us again. Okay, think it over, look at the reaction, and we'll talk about it. The answer is 2 moles. Okay, let's take a look here. In our basic chemical reaction, if we have 1 mole of this and 3 moles, we can form 2 moles of ammonia. So we have to have a mole of nitrogen, 3 moles of hydrogen reacting. Here, we still only have 3 moles, which is our minimum. Okay, that's the minimum that we need to form ammonia. We have twice as much nitrogen. Which is going to run out first in this reaction? Hydrogen, because that's our base. That's like the minimum that we have to have. So this is going to be in excess, and we're still going to be able to form 2 moles of ammonia. Because we needed 3 moles, and we have that, we still have 1 mole of nitrogen gas. So we're going to run out of hydrogen, and we're going to end up being at 2 moles of ammonia. Okay? So this is going to explain that a little bit. Okay, amount of H2 limits the amount of ammonia that we can form here. Okay, from the amount of N2 available, we could have made 4 moles, since it's double, but from the amount of hydrogen available, we can only make 2 moles, because we started with 3, and that's what we had to give. So we can only make 2 moles. So here, hydrogen is our limiting reactant. When in your problems you've seen that this compound is in excess, that's what it means here of this N2. At the end of our reaction, since we had twice as much nitrogen as we really needed, there's going to be extra nitrogen left over, which means it's in excess. Okay, it's left over at the end of the reaction. So there would be 2 moles of nitrogen left over, because we only needed to use, we only needed to use 1 mole, so there'll be 1 mole left over at the end. Okay? It's in excess. All right, let's take a look at this reaction. This is copper plus sulfur will yield copper sulfide. Okay, what type of reaction is this? Synthesis. Good. So what's the limiting reactant when 82 grams of copper reacts with 25 grams of sulfur? We want to find our limiting reactant here. So the process that we do here is we're going to do the problem twice. We're going to go from each of our starting compounds. So we're going to go from grams to grams of each of our starting compounds to our product. So we'll go from grams of copper to grams of copper sulfide. Then we'll go from grams of sulfur to grams of copper sulfide, and we'll see which of those will yield a larger product. Okay? These are 4 steps because we'll go gram to gram. So the reason that we can do this is we want to find out the number of grams of our product we would form if this copper was our limiting reactant. If this was going to be our limiting reactant, this is how much of our product we could form. And then we'll try it again for sulfur. If sulfur is our limiting reactant, this is how much product we can form. And we'll see which of those gives us a lesser amount of product, in which case that would be the limiting reactant. We've got to go gram to gram. Gram to gram. Okay, so we're going to start with our 82 grams of copper. So you'll have 2 T-charts for these chemical or these limiting reactant problems. From copper. Okay, so this gives us 102.6 grams of copper sulfide that would be formed if copper was our limiting reactant. So if copper runs out first, if that 82 grams of copper that we put in runs out first, that would be our limiting reactant, and we'd only end up with 102.6 grams of copper sulfide. So now we want to do it with sulfur. So we're going to start with our 25 grams of sulfur.
Thank you.
Do we agree? 124.21? Yeah, about 124. Okay, anywhere in that region. So what this is telling us here is that if we started with copper, 82 grams of copper, and we had excess sulfur, we would only be able to form 102.6 grams of our product. Vice versa, if we started with 25 grams of sulfur and we had extra copper, we'd only be able to form 124.2 grams of copper sulfide. So which of these do you think would be our limiting reactant? Yeah, copper. Very good, copper. Okay, so whatever T-chart gives you your smallest mass, you need to look back to the beginning of that T-chart, and that compound will be your limiting reactant. Okay? This is really important for you to see that just because the starting amount is smaller does not mean that it will be your limiting reactant. Okay, that's really important for you to see because 82 looks a lot bigger than 25. So we would kind of start to think that, oh yeah, sulfur is going to run out first. That's not the case. So you've got to make sure that you understand that just because it has a smaller starting amount, it does not mean that it will be your limiting reactant. Okay, so we got to do the T-chart to grams. Okay. Okay, we already did all that. All right, since the limiting reactant is copper, we can use that to determine how much product is formed. So the second question on that slide kind of asked, what's the maximum amount of copper sulfide that could be formed? Yeah, 102.6 or 103 grams. That's the maximum amount, because if we put those two amounts into our chemical reaction, the copper would run out after 82 grams, and that means we only will have formed 102.6 grams of our product, so that's it. Then the reaction is done. Okay, so that's the maximum amount of product that we could have gotten. This is magnesium plus hydrochloric acid will give us magnesium chloride and hydrogen gas. We wanted to find the limiting reactant when 6 grams of hydrochloric acid reacts with 5 grams of magnesium. Okay, we're looking for grams of product, and we want to find out what our limiting reactant is. So whenever you see a problem that has two starting amounts, an amount for each of your reactants, you got to do those T-charts, one for each. Okay, do a T-chart twice, one for each of those. And we want to find our smallest amount of grams that could be formed. That product will then be your limiting reactant. On this problem, does it tell you what to compare? If you have two products, how do you know which one to compare it to?
You just combine them.
If we want to go from HCl, what are we going to?
MgCl?
Yeah, you can do either one. You can compare either products. Exactly. You just have to be consistent and do, if you're going to go from Mg to MgCl2, you also have to go from HCl to MgCl2. You've got to go to the same product for both T-charts.
Wait, so what's the, like, the other one was Cu2S, what?
Exactly. You can pick which product you want to go to,
Okay.
but you have to do it the same for both T-charts. I would probably recommend going to H2 just because it's a less complicated molar mass. It does not make a difference. I guarantee you if some of you do magnesium chloride and some of you do hydrogen gas, we'll get the same limiting reactant. Okay? We won't get the same amount of product that can be formed necessarily because we're looking at two different products. Okay, do we kind of agree with our ratio here? Did everyone get that HCl should be our limiting reactant? Because it gave us a smaller amount of our product. So whether you choose to go to H2 or MgCl, for those of you that did MgCl2, did you have HCl as being your limiting reactant? You still got a smaller amount of product formed, right? Uh-huh.
Are those answers like rational to
Mm-hmm.
use MG?
Yep. Yep. Because we started with a pretty small amount of our reactants, and hydrogen does not weigh very much. So this answer makes sense. You probably got a little bit bigger number for MgCl2, right, as your mass. Okay. Yep. So if we put in 5 grams of magnesium and 6 grams of hydrochloric acid, we can only get out 0.16 grams of hydrogen. Okay, and then for those of you that solve for MgCl2, how many grams of, what was your maximum amount of product you could get out? Tommy and Ryan, what'd you have? Out of HCl. Mm-hmm. 7.83 grams. Okay. Okay. So which of these two was our limiting reactant? HCl, and then our maximum amount of hydrogen formed would be 0.16. Okay. If the question would ask you, what's the maximum amount of each product you could form, what would you then have to do? Once you find the limiting reactant, you just have to go back and do one more T-chart. You wouldn't have to do all four. Because once you found out that HCl is the limiting reactant, you could just do a T-chart from HCl to magnesium chloride. Does that part make sense? If it asks you for the maximum amount of each product, you just do a T-chart once, or do a set of T-charts to determine the limiting reactant, and then you can just do one more to find that maximum. Okay? All right. Try this one on your own. You have to build your reaction here and balance. You can do it. Okay? We're starting with ethylene, which is C2H4. It's combusted with oxygen, which has to be O2. Okay? And what are the products of a combustion reaction? CO2 and H2O. So that's how you start your building your reaction here. So we're starting with C2H4 plus O2, and we're going to get out carbon dioxide and water. So build that reaction and get it balanced, and then we can start the limiting reactant process. Okay, so here we should have gotten 15.6 grams if our ethylene was our limiting reactant, but we knew oxygen was, so we only can get 2.98 grams of carbon dioxide to be formed. Okay?